All right, well, let's just get back into stuff. I don't want to answer any homework questions so we can get to a point where you can work on some more problems. So last time we had just started talking about circular motion. Did I start that? Yes. And I said that the angular acceleration vector is the rate of change of the angle oriented, no, oriented perpendicular to the instantaneous plane of motion according to the right-hand rule. That's just sort of an intuitive thing. You're not going to, you're almost never going to have to use that. Maybe that's a little strong, but in this class, you're not really going to have to use that, but that's just understanding what the angular velocity is. And so then once you know what the angular velocity is, the angular acceleration it's also a vector, alpha. And that is just the time derivative of the angular velocity vector. In circular motion, the direction of the angular velocity, so if something's moving in a plane, okay, the angular velocity has to be perpendicular to that plane, so it's out of the page or into the page. And that direction is never changing, right? I mean, it can go from this to this, it can go from positive to negative, but it's always perpendicular to the plane. And so if the direction's not changing, if you take the time derivative of it, the direction has to be parallel to that. There's no other possibility. So in circular motion, alpha is parallel to omega. It doesn't have to be in the same direction. It can also be in the opposite direction. So what does it mean if alpha and omega are in the same direction? If they're in the same direction, then the rotation is speeding up. And if they're in opposite directions, the rotation is slowing down. Um, that's also the case with translational velocity and acceleration. Well, think of it, since this is circular motion, think of like a one-dimensional motion, like an object rolling along an incline or something that you throw straight up into the air. If the velocity and the acceleration are in the same direction, the object's speeding up. If they're in the opposite direction, the object's slowing down. And it works the same with circular motion. In spherical motion, alpha and omega are not parallel in general. And both change their direction in time. Over time. Okay, so spherical is a lot more complicated to imagine. But the equation that you use to represent the motion of a particle that's in spherical or circular motion are the same. The velocity of the particle is equal to the angular velocity crossed with this r vector. I'll tell you what that r vector is in a second. And the acceleration of a particle in circular spherical motion is equal to alpha cross r plus omega crossed with the quantity omega cross r. Where r is a vector from the center of the circular spherical motion to the particle. So that r vector, if we're talking about circular and spherical motion, the distance between the particle and the center of that motion has to stay constant. But that vector changes in time. Its magnitude is constant, but not its direction. So r has a constant magnitude but a time-varying direction. And in Physics 1, I'm sure you saw these equations, but maybe you more often use just the scalar forms of these. That's what I would guess. I mean, everyone does those a little bit differently. But this term is the tangential acceleration. And this term is the centripetal acceleration. So if you did this in a scalar form, you had the magnitude of the angular velocity times the magnitude of the angular velocity times the distance from the center to the object. That's just a scalar. and then it was pointed from the object toward the center. In this format, you don't have to think about those directions. You know, the cross products do the directions for you. You have to group it in this order because if you did omega cross omega, you'd get 0. So. All right. Let me do an example. So let's say there's a child on a carousel. And the carousel has a 2.0 meter radius. Possibly that doesn't affect the problem, but that would be a really big child. Yeah, right.
Well, no, it would affect it.
Well, his center of mass is going to be 2 meters from the center of the carousel. So we're still yeah. Daddy, why isn't my radius as big as yours? It will be soon, son. Keep eating those Twinkies. That's a self-autobiographical sketch. Yeah, right. I think more than once, right? I think it happens every once in a while, and then someone buys them. Exactly. It's such a big stockpile. So this distance is 2 meters. At a given instant, the angular speed is 2.5 radians per second. Which way do I have this going? Counterclockwise from above. Have you ever noticed that like whether something's moving clockwise or counterclockwise depends on. So in 2D it makes sense. In 3D you have to describe it pretty carefully because it's counterclockwise to somebody looking down from above, but clockwise to someone looking from below. And it's slowing down. An angular acceleration magnitude of 9.5 radians per second squared. So we want to calculate the velocity of the kid and the acceleration of the kid. And I'll use a coordinate system like this. There's the x-axis, there's the y-axis. Well, let me line it up with the kid. That's just like your opinion, man. So there's x, y, z. Okay, so he's 2 meters in the negative y direction from the center. Okay, so at this instant, and only at this instant, because that r vector changes, the r vector is 0, -2, 0. He's in the negative y direction from the center. Oh, by the way, the coordinate system, do we know whether that coordinate system is fixed, is holding that orientation as the thing spins around it, or whether it's rotating with the carousel? We do know that. Well, we do, but it's not intuitive. In order for us to use any of the methods in this chapter, the coordinate system has to be non-rotating. If you look back at the start of this chapter, like all of this stuff is particle kinematics in a non-rotating coordinate system. So there are ways to deal with it, and we'll talk about that later on if we did have to use a coordinate system that was rotating with that. But the idea here is that that coordinate system will still be oriented like that when the kid's over here. Okay, it won't be turning with them. Okay, what's the angular velocity vector? It's rotating this way. The angular velocity, we have the magnitude. All we need is the direction. And the direction goes according to the right-hand rule. So the angular velocity direction is the positive z-axis. Everyone see that? So the angular velocity is 0, 0, 2.5. And so the velocity vector is 0, 0, 2.5 crossed with 0, -2, 0. And so that is positive 5, 0, 0 meters per second. So now let's look at the problem and make sure that that makes physical sense. When the kid's right there, does it make sense that his velocity vector rotating this way would be in the positive x direction? Yeah, it does. It's going to be, the velocity is going to be tangent to that circular path, sort of in the direction of motion, and that's positive x. Any questions about that part? And then for the acceleration, r is still the same, omega is still the same. We have to figure out alpha. We know the magnitude of alpha, and we know this is a circular motion, so alpha has to be either in the positive or negative z. So how do we know whether the angular acceleration is in the positive or negative z direction? It's slowing down, so it has to be in the opposite direction of omega. And so, what did I say, 9.5. So this is going to be 0, 0, -9.5 radians per second squared. It's the opposite direction of omega because it's slowing down. And now we'll just plug that into the circular motion equation. The acceleration is equal to 0, 0, -9.5 crossed with R, 0, -2, 0, plus 0, 0, positive 2.5, crossed with the quantity 0, 0, 2.5, cross 0, -2, 0. This one is 5, 0, 0. And this one is -17, 0, 0. And so the total acceleration is -17, I think positive 7.5, 0. No, I don't. I have dot, dot, dot written. Meters per second squared. If you want to save yourself some time on circular motion problems, you can quickly and easily program these two things into your calculator. And so then all you have to do is punch in the components of the vectors and it'll do this calculation for you. There'll be a few equations like that that'll come up over and over again. So if you want help doing that, let me know. I can't remember if that's on the PDF of programs on D2L, but in the course information section on D2L, there's a PDF there that has the code for a bunch of calculator programs. Yeah, but I think you have to use a little different syntax. So let me know if you want help figuring out how to translate that. The approach is different. I don't know about the syntax might be similar, but you have to do things a little bit different, I know. But if you come to office hours, we can probably figure out how to do it. Yes? No. Yep. And it doesn't take long to punch these in. Yeah, right. No, that's a good question. I think if you don't program anything in your calculator for this class, you'll have plenty of time on exams. D-form is sort of a different story, but that's how it is in this class. D-form? In D-form, you're going to need programs in your calculator for all this stuff, or it's going to take a really long time to do the calculations. But in dynamics, you won't. In D-form? Yeah, that would be. You would get full credit for the one question that you answered. No, like handcrafted. Yes, did you have a question? Yeah, but this is just an estimate. Son of a. Yeah, exactly. That.
Oh, I missed 19.
To be honest, on a test, if you wrote this equation and then wrote -17, 7.5, I'd probably write some kind of hilarious comment and give you full credit for it. Yeah, yeah, for any problem. No, probably not. To me, I can guarantee. To you, no guarantees. On this, that would probably, if you didn't even punch anything in, that would probably depend a little on my mood, but I could see myself on occasion giving full credit for that, yeah. Um, this equation is what I call the watermelon equation. By the way, you see that in notes or whatever. So acceleration is equal to alpha cross r plus omega cross quantity, omega cross r. I always call it the watermelon equation because you can remember it as all ripe watermelons will rot. No, it'll all be given. Yeah, every important equation will be given on the test. Okay, so circular motion a lot of times is used in cases where the center of the circular motion is moving. So why is that? Because so circular motion we'll see is really important in dynamics because when you have rigid bodies, any point on a rigid body is moving in circular motion around a hinge. Okay, so if my elbow is moving like this, it's moving in circular motion around my elbow. Any point, if I'm trying to track the middle of my hand, it's in circular motion around my elbow. My elbow could be moving, like if I'm running or whatever, or if I'm doing this. But so that's a case where if we're trying to track the motion of this point and I'm running, I would need to know the velocity of this point, assuming that my elbow is still, and then I would just add that to the velocity of my elbow. And then you can keep going with that. Like, well, how do I know the velocity of the elbow? Well, the velocity of the elbow, I use circular motion to figure out its speed around the shoulder, and then add that to the velocity of the shoulder. And how do I know that? You can keep going all the way down until you get to the ground or whatever. So that brings up next topic, relative motion. Yes. So angular velocity and angular acceleration, those are in radians. Any function where you're taking, any function that has an angle that you're taking derivatives of has to be in radians. And other than that, it doesn't matter. But normally if I'm just describing an angle at a certain instant, I do it in degrees. Okay, so relative motion is, say that you're tracking the motion of a particle in two coordinate systems with the same orientation. So those coordinate systems have the same orientations. They have different origins. What's the relationship between those two measurements? You know, you get one measurement of the particle's location from one coordinate system and one from the other one. Well, if you draw this out, you can see that it's just, it just uses the definition of vector addition. If this is the particle t, and then here are the two coordinate systems, they have the same orientations, but I'll call this one coordinate system A and this one coordinate system B. Well, this is the location of P according to coordinate system A. This is the location of P according to coordinate system B. And you can see that if you use coordinate system A to track the location of coordinate system B, then vector addition says that what you see from A for P, you know, the position of P according to coordinate system A is equal to the sum of the position of P according to coordinate system B plus the position of that second coordinate system B according to A. Okay, that concept is, it's easy to see graphically like that, but the wording of it is cumbersome. So we need a way to describe these different things, what you see according to one coordinate system and what you see according to another one. And so the way we're going to do this is we're going to call this vector the position of particle P according to A. We'll use, so those are both subscripts, but we'll use like a fraction notation. The denominator type thing of the fraction is what you're using to observe it. The position, this vector is the position of P as seen by coordinate system B. And this one is the position of B according to coordinate system A. If this arrow is going the other way, yeah, that would be the position of A relative to, you know, according to coordinate system B. And by the way, that brings up sort of sometimes a useful fact that if you flip those two, it just makes it negative. You see that, like, if the vector is going that way, it's B over A. If you flip it that way, it's A over B. And if all you've done is switch the direction of that vector. And I'm teaching you how to do some calculations, but the main thing I'm trying to teach you how to do is not sound stupid when you talk to people. And so, when you talk to people about this, the way you say that is I think I blocked that out. It sounded so stupid. I don't even. But we call this the position of A relative to B. Okay, so that just makes it's not as cumbersome as saying the position as seen from coordinate system A, just a nice, concise way to say that. Position of this relative to this. And then what we get from that figure is, so that figure says the position of P relative to A is equal to the position of P relative to B plus the position of B relative to A. Okay, so that's the first relative motion equation. And then if you just take time derivatives of both sides of this equation, those give you identical velocity and acceleration versions. So it's also true that the velocity of that particle P relative to A is equal to the velocity of P relative to B plus the velocity of B relative to A. And then if you take another time derivative, same thing with acceleration. Acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. Now you could just think through that vector addition every time to make sure that your subscripts are right, okay? But as a time saver, you can use this memory device. Your subscripts are correct if the equation works as fraction multiplication. So like in all of these, if you just think of the subscripts, P over A is equal to P over B times B over A, because these cancel. And so if these are your subscripts for the relative motion equation, then you have it right. So why does that work? There's no reason why it works. It's just like someone noticed it works and it makes it easy to remember. It doesn't have anything to do with real fractions or anything like that. That'll be awesome. Yeah. RAM upgrade. Only memory things. Yeah. Here are the equations for the test. That's funny. Futurama is funny. I haven't seen that in a long time, actually. Can I still make it? Oh, no. Okay, so relative motion. One thing to notice here what are the two requirements for a coordinate system to be inertial? So inertial, by an inertial coordinate system, I'm talking about like what have to be the properties of the coordinate system if laws of kinetics like Newton's second law work? What kind of coordinate systems can you use Newton's second law in? There are two things that it can't have. One is the axes can't be rotating. If you ever, so if you had took a ball, and spun your chair around and dropped it, according to that coordinate system, you would measure an acceleration of the ball that would look like it was accelerating in a spiral. And if you use the acceleration of that spiral with what you know about gravity and put it into Newton's second law, it would look like Newton's second law was violated. Okay, that's because you have a rotating coordinate system, and that's not allowed. You have a non-inertial coordinate system in that case. So an inertial coordinate system has non-rotating axes. Yeah, the orientation is fixed. It can be moving, but it can't be rotating. And what's the second requirement? What's the other thing that would make it look like Newton's second law was violated? So if I'm thinking of like sort of my eyes as being the coordinate system, that's what's taking the measurement. So it would screw it up if my eyes are rotating as I watch this thing. And the other thing that would screw it up is if the coordinate system is accelerating, if the origin is accelerating. So the other requirement is that the origin is non-accelerating. Yep. Right. And it also has to be moving in a straight line. It can't be turning because that's also acceleration. Okay, so we'll have to wait till later to figure out how to deal with adjusting things measured in rotating coordinate systems, so you can use laws of kinetics. But we can now use the relative motion equations to correct for a rotating an accelerating origin. So the relative motion equations can be used to correct for an accelerating origin. Well, let's think for a second about how that works, I guess. Just like we thought about how it would screw up, it would appear to screw up Newton's second law if you're measuring acceleration in a rotating coordinate system. Now imagine taking so imagine being in an elevator that's in free fall and you drop an object. You know there's a force of gravity pulling down on it with a magnitude of mg, right? But what would it look like the thing is doing according to your frame of reference in the elevator? It would look like it's just hovering there with you, And so again, Newton's second law would look like it was violated. But if you know what the acceleration of the elevator is, you can correct for that by saying so if this is accelerating down at 9.81 meters per second squared, you probably have bigger things to worry about than physics experiments. But who has a ball? Who has a ball? Yeah. So yeah, it makes you feel like you're Michael Jordan. Yeah, I'm sure. Oh boy, that's challenging yourself. I'm gonna look that up right after a class. When I was a kid, I used to do gymnastics. I wasn't very good, But my club worked out where the U of Minnesota team worked out, and they've been phenomenal forever, and they had some just crazy people. And but there was this one guy who wasn't really like one of their stars or anything, but he was just like super powerful, and he stacked 36 inches of mat. 3 feet. That's like this, right? Half as tall as me. And did a standing backflip onto it from the ground. What? Oh, really?
So he jumped up to it.
Yeah, he was on the floor, did a backflip, and landed on a thing like a ninja. Yeah, exactly. Okay, well, anyways, so to calculate the acceleration of the ball relative to the ground, so this is inertial. You could use this value in Newton's second law. You would take the acceleration of the ball relative to the elevator plus the acceleration of the elevator relative to the ground. And now, so this is the measurement you take in the elevator that makes it look like it's hovering. Okay? But add it to what you know about the acceleration of the elevator, and now you have an acceleration of the ball that you can use in Newton's second law, and it works. Okay, let me just do a real quick example. So let's say, oh, I know what. Let's say now it's the same carousel problem, except this time the carousel is on a truck with an instantaneous velocity vector of, so let's say the truck is driving in the positive x direction. So 20, 0, 0 is the velocity of the truck, meters per second. And an instantaneous acceleration, so say the truck is speeding up, so 500. Now we want to know what's the velocity of the kid to an observer on the ground, and what's the acceleration of the kid to an observer on the ground. Well, the velocity of the kid relative to the ground is equal to the velocity of the kid relative to the center of the carousel plus the velocity of the center of the carousel relative to the ground. And velocity of the kid relative to the center of the carousel is what we got from the circular motion. Where is it? 500. So 500. The center of the carousel moves with the truck. So the velocity of the center is 20, 0. And so the kid at that instant is going 25, 0 meters per second. And B, the acceleration of the kid relative to the ground is equal to the acceleration of the kid relative to the center plus the acceleration of the center relative to the ground. Remind me what that was. Was that, what were the acceleration of the kid relative to the center? So that's like first 12.50. And then the acceleration of the center of the carousel is 500. And so you get negative 14, 12.50 meters per second squared. And since the truck is accelerating, if you treated the kid's acceleration as being this, it would screw up Newton's second law. But since the ground is inertial, if you correct for the fact that the truck's accelerating with the relative motion equation, you get something you can use in Newton's second law. Any questions about that?
Just because it violates the law, we come up with something.
Yeah, I mean, Newton's second law, like one of the requirements of any kinetics equation, any of Newton's equations, are that you have to use acceleration values measured in an inertial coordinate system. And so if your measurement is not from an inertial coordinate system, you have to use a calculation to figure out what it would be in an inertial coordinate system. In an inertial coordinate system. Inertial is good, non-inertial is bad. Okay, have a good weekend. No, see you in D form.